AI training data is quietly reshaping human history by scraping, summarizing, and replacing the records future systems will learn from. In 1959, a machine learned to beat its creator at checkers, not by following rules programmed in advance, but by playing thousands of games and learning from its own mistakes. Arthur Samuel's checkers program became the first machine to demonstrate something that would change everything: the ability to improve itself through trial and error. It's about a decades-long race to answer a question that connects animal psychology, Cold War mathematics, backgammon tournaments, a humiliating defeat of a Go world champion, and every AI breakthrough you see today. How do you teach a machine to want something? Because wanting, true goal-directed behavior, isn't just coded logic. And the path from Edward Thorndike's puzzle boxes in the 1890s to DeepMind's AlphaGo in 2016 is one of the most overlooked stories in the history of artificial intelligence. You're about to understand how machines learn to learn. Not through memorization, not through massive datasets labeled by humans, but through reward and punishment, exploration and exploitation, trial and error in environments they've never seen before. You'll see how a thread from animal psychology became the foundation of modern AI, how mathematicians in the 1950s built the theoretical backbone, how researchers in the 1980s struggled for funding during an AI winter, and how everything changed in 2013 when deep learning met reinforcement learning and created something the world had never seen. By the end, you'll know why this obscure corner of AI research became the key to superhuman gameplaying, robotic control, and autonomous decision-making. But first, we need to go back more than a century. Edward Thorndike, a psychologist at Columbia University, placed hungry cats inside wooden puzzle boxes. The cats could see food outside the box, but to escape, they had to pull a lever or press a latch, completely by accident at first. The first attempt took minutes of clawing, biting, and random flailing. Each time the same cat was put back in the box, it escaped faster. The behavior that led to reward, pulling the lever, was strengthened. Thorndike called this the law of effect. Actions followed by satisfying outcomes are more likely to be repeated. It was a learning algorithm written in flesh and neurons. And decades later, computer scientists would recognize it as the foundation of reinforcement learning. While psychologists studied behavior, mathematicians were building the other half of the story. In the 1950s, Richard Bellman developed the framework of Markov decision processes and published what became known as the Bellman equation, a recursive formula for calculating the optimal decision at every step in a sequence. It was abstract, theoretical, designed for operations research and control theory. But it gave AI researchers something crucial: a formal mathematical language for decision-making under uncertainty. An agent in a state, a choice of actions, a transition to a new state, a reward signal. This was the skeleton of reinforcement learning, waiting for someone to make it real. In 1959, Samuel, working at IBM, built a checkers playing program that didn't just execute pre-programmed strategies. Samuel's program used a method that evaluated board positions and updated those evaluations based on whether moves led to wins or losses. It was crude by today's standards, but it worked, and it became one of the first public demonstrations that machines could learn from experience, not just computation. Samuel's breakthrough was ignored by most of the AI research community. For the next 2 decades, artificial intelligence focused on symbolic reasoning, expert systems, and logic. According to Rich Sutton's foundational textbook on reinforcement learning, the field has a rich and interconnected history. The trial and error thread from psychology and the optimal control thread from mathematics evolved independently for decades. Sutton and his co-author Andrew Barto write that they first came to focus on what is now known as reinforcement learning in late 1979. They weren't trying to build game-playing systems or robots. They were trying to understand a specific problem: temporal credit assignment. If an agent takes 10 actions and then gets a reward, which action deserves the credit? This is the problem that animals solve instinctively when they learn. And it's the problem that stalled AI for years. He separated temporal difference learning from control and treated it as a general-purpose prediction method. Instead of waiting until the end of a task to update your predictions, you update them continuously, using the difference between your current prediction and your next prediction. It's how you learn to estimate how long your commute will take, not by waiting until you arrive, but by updating your guess as you hit each traffic light. Sutton's method allowed agents to learn online, in real time, from incomplete episodes. But it still wasn't enough to break into the mainstream, because throughout the 1980s, AI was in a winter. Funding dried up, hype collapsed. Researchers who worked on learning-based methods struggled to publish. Reinforcement learning, despite its theoretical elegance, had no killer application. Then in 1989, Chris Watkins completed his PhD thesis at Cambridge. According to Chris Watkins, one of reinforcement learning's pioneering researchers, the field emerged from contributions across multiple disciplines. Watkins realized that a natural way to think of reinforcement learning was as incremental dynamic programming by an agent exploring a Markov decision process. His algorithm, Q-learning, became one of the most famous in all of AI. Q-learning let an agent learn the value of taking a specific action in a specific state without needing a model of the environment. It could explore, it could exploit, it could balance both. And most importantly, it could learn optimal policies even in environments it had never been trained on. But the world still hadn't seen what reinforcement learning could do. In 1992, Gerald Tesoro at IBM built TD-Gammon, a backgammon playing program trained entirely through self-play using temporal difference learning, and it became one of the strongest backgammon players in the world, competitive with top human champions. TD-Gammon was the first major public success of reinforcement learning. But even then, the breakthrough was narrow. Backgammon is a game of dice and probability. It wasn't clear if RL could handle the complexity of deterministic strategy games like chess or Go. For 2 more decades, reinforcement learning remained a niche academic field. DeepMind, a London-based AI startup founded in 2010, published a paper showing that they had combined deep learning with Q-learning to create an agent that could play Atari games at superhuman levels. The agent didn't know the rules, it only saw pixels and a score. And it learned to play Breakout, Space Invaders, and dozens of other games just by trial and error. The US Department of Energy's research labs highlight deep reinforcement learning as a transformative evolution of classical RL. This was the moment reinforcement learning entered the modern era. Deep neural networks gave RL the ability to handle high-dimensional inputs, images, sounds, sensor data. Q-learning gave it the ability to optimize long-term strategy. In 2016, DeepMind's AlphaGo became the first computer program to defeat a professional human Go player, and then a Go world champion. The match against Lee Sedol, one of the greatest Go players in history, was watched by over 200 million people. A move so unexpected, so creative, that human commentators thought it was a mistake. Move 37 became one of the most famous moments in AI history. Proof that machines trained through reinforcement learning could discover strategies that humans had never imagined. The authoritative textbook used across universities, Sutton and Bartow's work, documents the major developments and key moments in RL history. In his comprehensive video lecture, co-author Andrew Bartow traces reinforcement learning from its earliest conceptual roots to modern applications. Reinforcement learning is now used to train robotic hands to solve Rubik's Cubes, to beat professional human teams in Dota 2, a real-time strategy game with more possible states than atoms in the universe. MIT's Cognitive Science Encyclopedia recognizes reinforcement learning as a foundational bridge between psychology and artificial intelligence. Reinforcement learning works when you can define a reward, when you can let an agent explore millions of times in simulation. But what happens when you try to apply RL to the real world, where exploration is expensive, dangerous, or ethically fraught? What happens when the reward function is ambiguous, or when optimizing the wrong reward leads to catastrophic outcomes? The history of reinforcement learning is a story of progress. 1. Trial and error isn't just biological, it's computational, and it unlocked machine learning that doesn't need labeled data. 2. The biggest breakthroughs in AI happen when separate fields, psychology, mathematics, neuroscience, engineering, finally connect. 3. Reinforcement learning proved that machines can discover strategies humans never imagined, but only when we define the right reward. And that's still the hardest problem. If you want more deep dives into the technologies reshaping intelligence, work, and power, subscribe now. Tomorrow, we're investigating the race to build AI that can reason, and why it's harder than anyone expected.